morning everyone. So now today let's discuss about the continuous system on the beam and Euler-Bernoulli beam and Timoshenko beam, and we will see in that how we can able to derive the equation of motion for a continuous system. So we will basically try to derive the partial differential equation for the Euler-Bernoulli beam, and we will see that how we can able to incorporate the other two things like the rotary inertia and the shear shear deformation in the Timoshenko beam. So let's start with that. So for the case of the Euler-Bernoulli beam, so if we see the beam theories, so beam theories is telling that like we have a beam now, that is like beam is a primarily a bending member. So the load application is normally the perpendicular to the main axis. So due to this type of loading, this actually get bended. So here if we see, the first theory tells that plane section remains plane before and after bending. So this means what? Like suppose we have a beam. Now if we take a cross section, so this cross section is like a planar line. So after bending, like suppose this becomes like this, after bending this will be like this. So again whatever was plane, that will remain plane. Second point is that neutral axis, so the section perpendicular, so section perpendicular to neutral axis remains perpendicular for Euler-Bernoulli beam, Euler-Bernoulli beam, but that condition can be relaxed in case of the Timoshenko beam. So for Timoshenko, it can be any type, means it can be of any angle, So by this, actually, like once we are saying that it can be of any angle, so with that we are actually incorporating the shear deformation. So let's see how we can able to do these things. So once we have this, now what we can do, can be of any angle. Okay, so now we can say that, so first case, let's try to derive that equation of motion. So let's think we have this axis, this is my axis, x-axis and y-axis, and we are taking, so we can assume that our beam was like this. Now the beam get deflected and like this way. So we are just taking a small section of the beam, so let's say like this, and if we try to apply, if we try to see in the left hand side, maybe we have the Vx, and in the right hand side we have V of x plus del V del x into dx, that we will get. Okay, and we are having some type of applied forces, maybe that is f of x, because due to that force that deformation is actually happening, and also, and this distance is the dx distance, and this deflection I can say that is maybe w. Yes, and we will also have some moment, that is mx, and we will have here mx plus del m del x into dx. So these are the force systems which are applied on that cross section. So now if we are try to do the force balance and the moment balance on these, so basically if we try to performing that summation of Fy equal to 0 and summation of bending moment at any point that is also equal to 0, then we can envision to get the governing partial differential equation of that system. So now if we try to see summation of Fy equal to 0, from there what can we able to write, that Vx plus f of x should be equal to Vx plus del V del x into dx. So del V del x into dx. So del V del x means what we can say, that in the right hand side the two shear forces are not equal. There is some type of changes are happening. So if we are thinking that change of the shear force is like increasing, so we are just thinking that del V del x is the slope of that, and that is happening in the throughout the length of dx. So we can say that del V del x into dx is the variation. So we will have this one, okay. And also once this thing is happening, this mass will get some sort of inertial force. So that one will be rho e into del w del t2. So we can also write that this plus rho e into del w del x2, so del w del t2. So that is actually telling what is the into dx. So that is actually telling how much like how much forces, how much inertia force that portion can able to get. So that is the total complete force equilibrium of that small portion. So now if we are cancelling this thing out, and for no force case, what can we say? We can say rho e del 2w del t2 dx plus del v del x into dx, that is equal to 0. So we can say del v del x equal to minus rho e del 2w del x2, so del t2, that we can able to see from the force equilibrium. Okay, so what next? We can equate the moment. So moment at which point should we equate? In those cases it is better to equate the moment from this point, which is the right side point. So if we are thinking that way, then what are the moments are coming? So we have the mx here. So we can say the anti-clockwise clockwise moments are mx plus vx into dx plus no plus, so now it will have a minus, so minus rho a del 2w del t2 dx into dx by 2. So that is acting at the dx by 2 distance, so dx by 2 minus mx minus del m del x into dx, that will be equal to 0. So that is the moment balance from the right hand side point. Now if we are thinking, so that can be cancelled out. So what can we get? So we can get dx dx minus rho a del 2w del t2 dx into dx by 2 minus del m del x into dx, that is equal to 0. So if I remove the dx, I can get vx minus rho a del 2w del t2 into dx by 2 minus del m del x, that is equal to 0. Okay. So here we can get the, after balancing the moment, we can get the equation number 2. So equation number 1 is stating how we can able to balance the shear force, and equation number 2 tells how we can able to balance the moment. But now here one point we have to understand that in this equation, in the equation number 1, if I see that we have the term rho a. So these two terms are related to the cross section of the beam. Like one is the cross sectional area and another is the material property. Sorry, not the cross section. So rho is the material property, mass density, and A is the area. W is the deformation or like how much means what where is the deflected shape is actually, so that is W. V is the shear force. So now you see that V is the shear force, we don't know, and W also we don't know. And if we are coming back to the equation number 2, where we are balancing the moment, in this case we can able to see we have again this term V, we have again the term W, which is the displacement, and we have the term moment. So there the three terms are present, which are basically unknown. So now our target is first, once we are talking that to derive or develop the governing differential equation, what we are actually aiming for? We are aiming to make or means write the equation completely in terms of the unknown variable, that is W. So we are envisioned to solve for the W. So our target is to solve for W. Okay, so we try to solve for W. We are not trying to solve for any other parameters. So what should be our target? Now we have to achieve this target. We first try to write bending moment in terms of W, and shear force also in terms of W. Okay, so if we see that equation number 2, that portion, now if we concentrate, this is the term of the rotary inertia, because that is telling that how the means here we are actually considering the rotational part of the inertia point. So that is there. So in Euler-Bernoulli equation we are neglecting that rotary inertia. So once we are neglecting that rotary inertia, then for Euler-Bernoulli case, what can we write? We can write Vx equal to del m del x. So that becomes for the Euler-Bernoulli equation. Okay, now if you see the Lord Rayleigh, he actually considered that rotary inertia. So in that case, if you are trying to derive for the Rayleigh beam, in that equation of motion, you have to stick to the full equation of the equation 2. You cannot able to reduce it like this way. And also Timoshenko, that is also like a full equation, complete equation is there. So this way this thing is coming. Okay, I hope there is no question on that. Good. So now if we try to see that what we have obtained, so here, so what we have obtained from here, if we try to look into that, we can see that in our one equation dv dx equal to minus rho a into del w del t2 and this one. So our target is to removing m and v, as we discussed already. So in one case we can easily able to remove it. So now if we are substituting this one here also, what can we get? We can able to get d2m dx2 should be equal to minus rho a d3w dt square into dx. That we can able to obtain here. Means if I just substitute this equation here, we can able to go like this. Perfect. So now let's see. So here now it is very clearly understood that we have to calculate for the mass only, nothing else. So now if we try to calculate for the moment, so not mass, that is the moment. So now if we try to calculate for the moment, how can I able to do that? Like let's say that was my deformed shape, and in this thing if we are trying to check that was the undeformed, and after deformation that again plane section is remain plane before and after bending. So what can we say? That my rotation, that is del w del x, is here. Suppose we are taking a particular point which is at the z distance, so that point has undergone to a displacement u, so my u will be equal to z into del w del x. Okay, So what will be the strain? Strain will be equal to del u del x. So strain will be nothing but z into del 2w del x2. Okay. Now if this is my strain, how much will be my stress? Stress will be E into z into del 2w del x2. That will be my stress at particular location z. That is also at particular location z. So now if we try to see that the cross section of the beam has a width of b, and as the section is like a uniform section, so we can say that the bending moment, the neutral axis will be from the center. So neutral axis is going from the center, so that is nothing but d by 2. So we can say that my strain block will be like this, and my stress block is also similar. So what will happen? So from the stress block we can able to calculate that is my T force is coming on top, and the compression force is going like this way. So how much is the T? So T will be equal to half of, that is my full force at the top fiber, and that is the distance d by 2. So that is d by 2 into the full force at the top fiber. So half into d by 2 into full force at the top fiber, that we can able to calculate like sigma d by 2 into its width. So that is b. That will be my full force at the top. So that will be 1 by 4 d into Ez, not Ez. So there it will be E into d by 2 into del 2w del x2 into b. So what can we write? E into b square by 8 into del 2w del x2. So that is the amount of tension force acting there. Now how much is the moment? Moment will be E into b square by 8 into del 2w del x2 into that distance. So that is, if we try to calculate from top, that will be at d by 2 into 1 by 3. So that will be d by 6, and from bottom again it will be d by 6. So that portion will be d minus 2 into d by 6, that will be d by 2d by 3. So that will be 2d by 3. So we will get like this. So we can get E into bd cube by 12 into del 2 del x2. So that means nothing but I. So E into I into del 2w del x2. So now if we are going back here, what can we able to see? That my del Sorry, here I made some small mistake. That will be not like that. Here just I substituted this one, so this will be this much only. So if I just substituting it again here, so what can I say? Del 2m del x2 should be equal to minus rho a into del 2w del t2, and my m is nothing but this one, so I can get EI into, or maybe equal to minus rho A into del 2w del t2. So that become my complete partial differential equation. So here you can notice one thing, like if the cross section is varying with the x, we can also able to consider it like this way. But if it is a uniform cross section, then means I of x is become a constant value. We can then able to rewrite it in a much more simplified form, is like this. That will become my Euler-Bernoulli equation of motion for the uniform cross section. So any question up to this before we proceed further? Okay, as there is no question, So I assume like okay, it's now understood. Good. So now let's go for the next one, that is the Timoshenko beam. So after completing the Euler-Bernoulli beam, now let's come to the Timoshenko beam. So now if you see in Euler-Bernoulli beam, we have ignored the rotary inertia, and additionally we are assuming that plane section like which is perpendicular to the neutral axis will remain perpendicular before and after bending. So if you see where that two theory were working, so this is the portion where actually we have considered that once it is perpendicular to the neutral axis, it will be remain perpendicular. So if that is no longer remain perpendicular, then this portion there will be some alteration. Okay, because then that u calculation will be no longer just only z into del w del x. So that u will be changed. Okay, and on the other hand, if you see, if we are incorporating the rotary inertia in this one, that will also change the main equation of motion, that is vx equal to del m del x. So these 2 points we have to so these 2 points was directly considered in case of the Timoshenko beam, but previously means before that, before Timoshenko, there is a Rayleigh beam theory. So in the Rayleigh beam theory, they have considered this portion. So suppose just let's do the Rayleigh beam theory as well. So if we say that Rayleigh beam theory, so Rayleigh beam theory, so that is actually telling Vx minus rho a into del w del t2 into dx by 2 minus del m del x minus del m del x, that is equal to 0, and another one is that dv equal to, and another one is that dv dx equal to minus rho a equal to minus rho a into del 2 w del t2. So these are the two equations coming in case of the Rayleigh beam theory. And so, and again, if we are looking at our aim will be this one. Uh, yeah, no. No, 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 no. So aim equal to EI into del W del X2, that is there for like once the plane section will remain plane before and after bending. So that portion we can able to get. So we are just putting here m equal to EI into del 2 W del X2. So that portion is there. Now this is coming here. So we can able to write V minus rho A del 2 W del T2 into dx by 2 minus del x EIX del 2w del x2, that will be equal to 0. Derivative with respect to this, then I will get dv dx will be minus rho a now I can just substitute it here. So all those things will become now if we are going to the Timoshenko beam, so in Timoshenko beam what will happening, we are having that beam. Now suppose due to the load the beam is getting deflected, And here, if we see, the plane section will no longer remain, means the plane section will no longer remain perpendicular, which was before. The after bending, it is no longer remain perpendicular. So there is some sort of shear deformation term present into it. So some shear deformation term is present into it. So now let's do that problem using the energy method, so that it will then encompassing the complete way that how we can able to do that in the energy method, and also how we can able to, already we have seen how we can do the force balance and we can able to solve it. Okay, so we can say that like the x-axis, so this is x, this is y, and that may be z-axis. So in the x and z there is no deformation because we are considering only the beam element. So x and z there is no deformation. So we can say that u is equal to 0 and v is equal to 0 and w is only equal to w of x by t, and just assuming that w is the vibration in the y direction. Okay, so what can I say, that the strain component epsilon xx will be equal to del u del x, that will be equal to 0. Then if I see that strain in epsilon zz, that will be equal to del v del, or we can do one thing, we can just make it z and this is y, so we can just, so that will make our life easier. So y that is equal to v and x that is equal to 0, del v del y that will be equal to 0, epsilon zz that will be del w del z that will be also 0, because it's a beam element and there is no component of del w del z. W is only the function of x and t, not the function of z. Now epsilon xy that will be equal to, that is with y plus del v with del x, that will be also equal to 0. Epsilon yz that will be equal to del v by del z plus del w by del y, that is also equal to 0. Then epsilon zx that will be w by del x plus del u over del z, that will be w del z. So that is only the thing, that is the only thing which will be there. All other terms are becoming 0. So this is the only term which will be left. So from here, what can we say? That sigma xx equal to sigma yy equal to sigma zz equal to sigma xy equal to sigma yz equal to 0, and sigma zx that is equal to g times epsilon, this one is equal to g times del w del x. Okay, so that can be written in more precise manner, because we know that once we are putting some sort of like some particular section if we are taking, then this is not only g times this, there is some sort of shear coefficient, shear correction factor is also incorporated. So the correct way of writing that is k times g times del w del x. So that is the correct version of writing it, where k is the shear correction factor. Okay, we got that. Now if we are writing the total transverse displacement of the central line of the beam. So suppose let's say our beam was like this. Okay, so where my P and Q was like 90 degree with the x-axis. Now what happened? First we think that there is some shear action happening. So maybe I'll just draw it with the red. It's some shear action happened, and so then if there is a only shear action happening, so then it will be like this. So my PQ will be shifted, and it will be shifted how much? So if I try to find out that position, so that will be your W of S, that is the due to shear. So that is the WS. And if we think that another point it is happening due to the bending, so once it will bend, in that case again it will have like a so due to bending, what will happen? Our PQ line will be perpendicular to the neutral axis, will be remain perpendicular to the neutral axis. But here PQ line is no longer. So here in the during the shear, PQ is not perpendicular to the neutral axis, but here it will be perpendicular to the neutral axis. So that will be coming the WB, W bending. So if I try to write the total W, the total W will be WS plus WB. Okay. Now if I try to calculate the total slope, then that will be W of this will be WS WX plus WB WX. That will be the total slope. Now the cross section of the beam undergo to rotation due to the bending only. So the cross section, if we try to see, that cross section can only be deflected due to bending. So the slope of the cross section, so slope the cross section, so rotation of the cross section, so that is on phi. So phi equal to del V over del X, that we can only see, because you see that once we are doing the shear, then the cross section is just like sliding, it is not rotating. So the rotation of the cross section can only happen once we are having that like rotational cross section happen only for the bending case. So you can write that rotational cross section is only with this bending. Okay, so what can we say? That is phi equal to this much, that is equal to del W over del X minus del WS over del X. So we can say that del W over del X minus beta. So where beta is the shear deformation of the shear angle. So beta, if we see, now beta equal to what? WS over WX. And if we see, this is how it look like. It is looking like this. Exactly. And that is nothing but your shear deformation angle. So that is the angle of the shear deformation. Because if you see that this portion is deflected by how much? This portion is deflected by WS amount, and that is my X. So the slope will be del W del X, del WS del X. So that is equal to beta. So this beta is nothing but the shear deformation angle. So we can able to write that phi will be equal to del W del X minus beta. So that is one of the relationship we can able to establish from here. So now if we try to see that how much will be the axial like a strain, what we have calculated in the last time also, like once we do that like a strain block, if we try to able to make, so we need to calculate that how much axial deformation is coming due to that bending. So how much axial deformation is coming here? So there, now this, so that is my U. So U equal to, it is only the total. So u equal to z into del w del x. Oh no, sorry, that is this into phi, which is the total rotation. So z times phi, and phi is how much? With a minus sign. So phi is how much? Phi is del w del x minus beta. Del w del x minus beta. Okay. So we are having u equal to this. Sorry, v equal to 0 and w equal to w of x comma t. So now let's see. What can we say? Epsilon xx. That will be nothing but del u del x. So we can say that will be minus z times del phi del x, and epsilon yy, that will be dv over del y, that is 0, epsilon zz, that will be del u over del z, that will be equal to, that will be also equal to 0. Okay, epsilon xy, that will be del u over del y plus del v over del x, del u over del y, del u over del y, you can say that will be also 0. Then epsilon yz, that will be del v over del z plus del w over del y, that is also 0. And epsilon zx, that will be del w over del x plus del u over del z, so that will be del w over del x only. Del w over del x and del u over del, okay, so del u over del z. So now del u over del z, if you see, so from this equation what we can get, we will have minus 5. So we will have just minus 5. Okay, so that we can able to get. So from here, what can we say? Sigma xx will be equal to E times sigma E times epsilon xx, that will be minus of E times z into del phi over del x. Okay, sigma yy, sigma zz, sigma yy equal to sigma zz equal to sigma xy equal to sigma yz, all will be equal to 0 because they do not have any other stresses, so that will goes to 0. So sigma zx, that is the only another term we have to check. It will be coming k into g into epsilon zx, k into g into epsilon zx, and now if you see k into g into del w del x minus phi, that will be my solution for these two things. Okay, we get that too. Now, so now what we can able to see, that more or less all of our stresses are obtained. Now after that we have to perform, we have to calculate the strain energy. If you remember that class where we have done with the Hamiltonian principle, we have first calculated the potential energy and kinetic energy, and from there we try to develop the equation of motion. So let's try to do it here for the continuous structure so that it will give the better understanding of the full thing. So first we try to calculate the potential strain energy. So that is pi equal to half of integral. So we are doing the volume integral here. So volume integral, how we should do, sigma xx, this into epsilon xx plus sigma yy into epsilon yy plus sigma zz into epsilon zz plus sigma xy into epsilon xy plus sigma yz into epsilon yz plus sigma then zx into epsilon zx, that full thing with a dv volume integral that we have to perform here. So now here this thing can be rewritten in that way that we are doing it from 0 to L, which is the domain, and then we will have like a area integral. So in that case we can start substituting the full thing. So this is the stuff where we can able to substitute. So that will be minus Ez del phi over del x into, again it will become z into del phi over del x plus that we have substituted here. First term we have substituted, multiplying this two, then 0 plus 0 plus 0 plus 0. Now the next one, that will be kg times del w del x minus 5, okay, into again del w, so this will be square of that term, okay. And that one, first like we will do the area integration and then we will perform the lengthwise. So now if we see that if we are performing the area integration on that one, then what can we get? So just let me rewrite the full thing there in the next line, and there will be half of 0 to L, then 2 times area integral of Ez square del phi del x whole square plus kappa g into del w del x minus 5 whole square dA into dx. Okay, so from the first thing what can we get? So if we do the area integral of that, this will give me E times I times del phi del x whole square plus kg into kga into del w del x minus phi whole square dx. That will be the solution coming. Okay, any doubt up to this stage? Okay, so if there is no doubt, then we can go ahead further. So that is my potential energy or the strain energy. Now what about the kinetic energy? The kinetic energy T we can able to get with half of 0 to L, then rho A into del W del T whole square, which is the velocity square. So that's the mass into velocity plus rho into I into del phi del T square into dx. So that is my T. Okay. And what about the externally distributed work done? That will be force, and then for that the work done, that is this much. So now if I see the extended Hamiltonian principle, so from the extended Hamiltonian principle, so how it comes? it will be 0 to L pi minus t minus w over dx should be equal to 0. So now if I substitute the full thing here, what can I get? I have the time. No, sorry, this is the time. That is t1 to t2. That is t1 to t2. Sorry. That is not with respect to x, that is with respect to time. So t1 to t2. And then we are performing the full integration 0 to L minus half of 0 to L rho A del 2 W del T2 whole square plus rho I into del phi del T whole square full thing with dx minus W and it will be equal to 0 to L f of W into dx into dt, that will be 0. With a okay, if there is no doubt, then let's proceed further. So from here, if we perform the integration by parts, so performing integration by parts, we can able to get, we will obtain integral ei del phi del x into del of del phi del x dx into dt equal to integral t1 to t2 ei del phi del x phi 0 to L minus 0 to L this into ei into del phi del x into del of phi into dx into dt. Okay, and second equation, what we can get? Second equation we can get integral t1 to t2 again 0 to L kag del w del x2 minus phi into del w del x into dx into dt, that will be equal to t1 to t2 kg into del w del x minus phi this 0 to L minus 0 to L kg into del x So these are the two equations we can able to obtain. Maybe I just number it like 5. Because it will become T1 to T2, 0 to L, rho E, del W del T, to del W del T, dx into dt should be equal to minus T1 to T2, 0 to L, rho A, del 2W del T2 into del W into dx into dt. 7 minus from all these we can finally able to derive that one, that the minus del x into kg into del x of del w del x minus 5 plus rho a into del 2w del t2 equal to f of x comma t, and another one will be del w del x into ei into del phi del x minus kg into del w del x minus phi plus rho I into del 2 phi del x del phi 2, that will be equal to 0. So these are like 9 and 10 are the two main equations for the Timoshenko beam, where you can see very interestingly, now you can see very interestingly that your now in the Euler-Bernoulli case we have only one unknown parameter, that was W, but here instead of a single unknown parameter we are having two unknown parameters, that is W and phi. So these two parameters are become unknown now. So once we are solving, we have to solve for obtaining these two parameters, and also we need to check that how the boundary conditions are changing. So there also means, if you see that and for the bending case, that will be, so for bending case, if I just see for bending case, your that will be nothing but your bending moment, that will be your bending moment, and your shear force will be kg into del w del x minus phi into del w, so that will be your shear force. So these two things we have to remember, and once you are doing it, we have to understand that and do it properly. Perfect. So any other question? No question. Thank you.